The objective today is to describe the basic process of encrypting data using public key encryption. Today's lesson is easily one of my most favorite of them all. Like today's topic took me really long to figure out, and I tried my best to simplify it so you can feel comfortable with your understanding of the objective, that is, how public key encryption actually works. So think back to that widget we used before and how not typical that thing was. That's not your typical math equation that you work with. Here's some more details. If you're looking for a times something mod 13 equals 1, for example, what you are really trying to find is a number that you could multiply by a. That comes out to be a list of infinite values. But using a very systematic approach, you can eventually figure out what the other person's secret is. So before we dive into the complex math, let's do the simple math first. Guessing input is hard. Using a clock size of 101, I'll give you the value for a and even hold the result of the modulo operation constant. Your task would be to find the value of b that makes the math work out. So let's do the first one together. Go to the link here, and if you're in my class, I'll paste that on Canvas. So I'm going to make my modulus 101. And so I have to figure out a way to make this clock say the number 1. So 2 mod 101 is 2 all by itself, but I'm supposed to times 2 times something, mod 101, to get 1. So what if I did 2 times 6? That would be 12. Does that come out to 1? Okay, so notice that any number smaller than 101 will be the number that it comes out to. So I sped up my clock here so I could do work faster. Let's say 2 times 200. Alright, now 2 times 200 is 400, and that gives me a huge number. Alright, let me try to simplify this. What if I did 102? Oh, that's easy. And then thinking about math patterns, I could go with maybe 204. If I just double it, will it give me the same result? No. However, if I'm only off by 1, if I make it 203, there we go. And then let's try to stay away from fractions because we don't want to go with that number 203. So when you're done with that, check your answers against this. You can also Google Modulo Calculator or go to this tool, or of course the widget that we use in class. So takeaways from that little exercise. Solving modulus equations like 2 times something is hard because you can't solve it like a typical equation. There are no easy patterns or shortcuts like other equations you might have seen in math class. As you've learned in step 1, there is an infinite list of single values for which you can put into this equation. At the end of the day, you'll end up randomly guessing to find some number to multiply by 2 that gives you a result in this list. So that's the thing that stops hackers, is the idea that the best chance they have at breaking encryption is by guessing random numbers, which they do. That's called brute forcing. You can keep guessing, but typically it's really difficult to do. Okay, so here's where things get especially hard. And they are especially hard when you use prime numbers as the clock size. So thanks to some special properties of prime numbers with a prime clock size, there's only one solution to each modulus equation. With a brute force search, you could go through all of them in a couple minutes, but what if the clock size were a 50-digit prime number? That's when you have encryption. Whenever you have a problem for which the only way to solve it is randomly guessing or brute force search over a large range of values, you have a candidate for encryption. So this is where things get really tricky. I try to come up with this outline, especially for you math types out there. Maybe if I explain this in the sense of balancing an equation, you might feel a little bit more comfortable with what's going on. So before we go to that widget, let me just explain what you're about to see. You're about to see 2 people using something called key pairs. In this scenario, pretend a guy named Bob has a secret. So Bob's job is to create some sort of public number. He's going to do that by taking a public key, so everyone knows this number, and he's going to times it by a private key that he doesn't tell anyone about. Then he'll do modulo using a public modulo number, okay? and that will give him this public number that he can pass to Alice. So now Alice is sitting there. She has this public number from Bob. She's going to times it by a private number that she has. She's not going to reveal it to anyone. Then she'll do the modulus with the same one that he did, so same public modulus, and that will give her his private number right over here. And imagine if that's the only thing you needed to get was just a single number. If we're talking about a Caesar cipher shift, then you have that number of how much the alphabet is shifting, and then you got it. You got the ciphertext. Then you got it. You could break the ciphertext and read the message inside. Now, it's a little more complicated than that, but just to feel comfortable with what we're talking about in class at such an introductory level, go with this. Go with this idea that Alice, the one trying to get a secret from someone else, all she needs is this equation, which is a balanced equation. You have a public and a private number, and then you have a public and a private number. If this is balanced, she'll be fine. And for Bob's case, he has 1, 2, 3 public numbers he's working with, but that's because he's the one sending a secret out into the public. So it's a little trickier on his end, but still very secure. And then if you want to take the hacker's perspective, think about guessing at this private number right here or right here. Either way, if you guess a number that's different than the actual number, you're going to get a different private key at the end. So when you guess a different number, you get a different number, and thus it's worthless. So don't get tripped up on the math today. What I'm saying is, like, this is math magic. This is what's allowing our world to work in such a crazy way. Now, quantum computers can easily break this. That's something we have to think about. So technology is going to need to change with that in mind. And at the end of the day, for the people, the students who are really understanding what's going on here, I would say, like, this is the kind of stuff that's only for the most powerful wizards and sorcerers to use. If you can understand magic like this, you might be able to create the magic like this that we will need in the age of quantum computers. I would love to talk more about post-quantum cryptography, but for the scope of this class, we just don't need that. All right, so let's go back here. We're going to use this link to see all these equations in action. Okay, so here we are. Now, I clicked all because I think this is the best way to approach this widget. That way you have plenty of time to think. You can write notes on a piece of paper to try to work this out. You could take notes on the formulas I just showed you over here. So let's put what I said into practice. Bob is the guy with the secret. So Alice wants that secret. Let's say Alice and Bob agree to a number, let's say 11. It could be any prime number here. So we're going with 11. So he takes that number and he's going to, so she has that public modulus. She'll go ahead and pick a secret key. I'm going to go with 5 here. So now we go over here and he needs a public key. Where does he get that? Well, from Alice. She's going to come up with the number 9, and then again, everybody can see it. So here's our Eve, the eavesdropper. So far Eve knows that the public modulus is 11, the public key is 9, and then she doesn't know anything else yet. So Bob comes over here, and he's going to pick a secret number of his own. Let's go with 5. So Bob takes this private key and the secret number, times them, modulus 11 them, and that will give him this public number. Number 1. He's going to go over here and give that number 1 to Alice. She takes that. She uses the public number and her private number, mod, public modulus right here, and this will give her Bob's secret number, 5. Is it correct? It is. And that is basically how public key cryptography works. So pause and rewind that section as much as you need to. I would feel really good today if you walked away with the knowledge of public key cryptography working because of the magic of math. And if you at least remember Alice's formula, Alice is going to have a balanced formula there. I think you could figure out any type of quiz question you would get about public key cryptography. So let's take a moment right here to narrow down what do you actually need to know. Cryptography has a mathematical foundation. It relies on asymmetric keys, which you can make using numbers and math. The modulo operation acts as a one-way function. When you multiply big numbers and mod them by other big numbers, it's really hard to figure out what the original numbers were. The technique is essentially reduced to random guessing. The security of publicly known encryption protocols is based on the fact that cracking a message by brute force would take an unreasonable amount of time. With a sufficiently large modulus, say 256 bits, which would be roughly a 77-digit number, random guessing would take an unreasonable amount of time. We're talking hundreds of thousands of years, depending on your hardware and your approach. Because the method of encryption is public, it actually increases the security because good guys and bad guys know how hard it's to crack. Your think right share here is, why is publicly known encryption protocols more secure than symmetric encryption? And I'll give you an assist right here. The idea that revealing encryption protocols allows everybody to take a whack at it, that's why it's so secure, because everyone's had a chance to try to break it. And the first time somebody figures that out, they're going to be pretty proud, or there's a bounty for them to earn money, and they will go ahead and make that public, the fact that they broke that public encryption protocol. Now, what made the encryption harder or easier for Eve to crack? Perhaps obvious, but the bigger the clock size, the harder it is for Eve to crack this. You know, the less guessing she has to do. There are also certain values that Bob could send, like 0 or 1, that would give away the secret. There is no way to crack the encryption other than brute force. If you could imagine that value being not a 4-digit number, but say a 75-digit number, the computation for Eve becomes mind-boggling hard. This is, in fact, how HTTPS works. It uses public key cryptography to establish a secret key between two parties. Once established, it uses a much faster encryption method for sending everything else. This is as far as we're going to take the public key analogy. The public key crypto widget is a superficial version of RSA encryption, and instead of basic multiplication, RSA uses numbers raised to powers of large prime numbers, very large, 256-bit. Prime factorization is a much harder computational problem to solve than our little multiplication plus mod problems here. So needless to say, it does get even more complex. But basically, if you know how to add 2 plus 2, you can add 5,000 plus 2,896, even though those numbers are more complicated numbers. Your think right share here, what's the difference between our widget on code.org and the very popular RSA algorithm? The numbers we let you use for modulus are all prime numbers. Prime numbers are useful because no numbers divide them, except for 1 in themselves. Modulo is a form of division, so if we only divide values by prime numbers, the results will be unique and distributed evenly over the range of possible values. Think right share, why are prime numbers essential to public key cryptography? Here's a nice little list of prime numbers for you. I like to pick my favorite NBA and NFL players based on if their jersey number is a prime number. You see any famous jersey numbers here? Maybe right here. Now, if you want to read an interesting article about unbreakable codes, the Voynich manuscript is interesting, so you can go to this link, Unwired. There's a lot of unsolved breakable or unbreakable codes out there, so unsolved codes, and sometimes the reward for solving them could be gold. You got creepy love notes in this website, astrological significant things like maybe even aliens, Soviet spy stuff, murder, and more murders. So some of those serial killers in the past have created some codes, and even today we haven't broken them. So I really like this particular article. Now, I'm running out of time in this lesson, but just to cover a couple interesting codes out there. This Cryptos at CIA headquarters, if you can break this code right here, you might get a NSA or CIA interest going for you. So if you need additional resources, you can go to this Google document. They break things down similar to how I did with the equation stuff. Now, as we're leading up to the DOL here, I kind of wanted to prep you. Maybe instead of using Alice and Bob, you can go with Ray and Ren. And then, of course, you would have Supreme Commander Snoke instead of Eavesdrop Eve there. And if you've seen this movie, The Last Jedi, you'd totally understand why I'm talking about somebody like Ray and Ren needing to communicate without Commander Snoke's knowing what that communication is. So, seeing how we're at the end of the lesson, and you can even replace the word programmers here with cryptographers. So what will these look like when we have a cryptographer that is open-minded, a risk-taker, etc.? So think about that as you answer this question. Which one of the IB attributes would apply to today's lesson? And so here's the DOL. All you have to do is try your best at answering this question. Why is public key encryption hard to crack? I'm looking for lots of vocabulary in your answer and maybe even a math equation or two.